Howdy and welcome back. So we're going to continue today's lesson with a brief example on serializing and deserializing in the binary format. The objects that we're going to be working with today are going to be of type student, which are simply going to be a type that contains two character arrays to store a first and last name of some sort of student. We're going to keep it simple. It's going to be a struct, and we'll be able to create objects such as, I don't know, myself as a student, or probably McBubster, my cat, as a student. One important thing to point out here is we are using C-style strings to store this information, and we're capping this at 255 characters. The reason why we're doing this is that we want each of these objects to have to be represented with the same number of bytes. And one of the reasons why we want to do this is that when we get into the binary file, if these aren't variable sized and they're fixed width, it's very easy to jump from one student object to the next in either the file or the memory, because they're all going to be of the same size. And if, say, Michael is longer than Bubby, it doesn't really matter because we've still allocated the full 255 characters to that first name field. So this is where, when I was talking about the plain text fixed width format, where I said this will kind of resemble some of the things we're doing with the binary format here. So yeah, and this is, again, just the context and application we're using as the example. It keeps the format simpler. And remember, we could have had these variable width, and we could have made this structure a lot more complicated. We would just need a more complicated map to ensure that, okay, maybe at the start of the student object, you had some integer values that would tell you how big each field is, and then you could use that information as you're jumping from one to another, or to actually get into its representation and find the correct stuff. But keeping it simple here, everything's going to look the same. Each of these data members are going to be the exact same length in memory, irrespective if that's completely consumed or not. So, serializing, deserializing in binary format. Let's just focus first on creating a record. And again, all of these kind of CRUD operations that we'll talk about, create, read, update, delete, are going to be context dependent. I could have defined this in a different way. I could have multiple different ways to create records into my binary file. There's a number of possibilities, and I'm just showing one here. So really, take that home and understand that. So the file that we're going to be interacting with is going to be called data3.dat. And what I want to do is have a create function that allows me to append objects of the student type to the end of a binary file. So we'll do this just kind of in unison. We'll append the first student, then we'll append the second student. So in this case, me. Second one's going to be my cat. We could have defined a function that would allow us to take a collection of student objects and append each to the end of the file. That would have been fair. There's a number of different ways how we could insert a record into this binary file, and we're just going to focus on appending first. So in order to do that, I have created this append student to file. It's going to take a file name, and then it's also going to take a student object by, could have been, I guess, constant reference, but by reference here. We'll then go ahead and create a output file stream. It's going to be bound to file, which was passed by constant reference as a parameter to this function. And then the mode is going to be both binary as well as append. So in this case, what we're saying is if this file already exists, we're going to append to the end of it. More so, what we're going to append to it is going to be in binary. And then all we're going to do is so at that point, we open the file, and the pointer that's pointing to the right location is going to be kind of one past the last element, and it's going to be waiting there for us to write. Obviously, a bit more is going on behind the scenes to make this illusion that we're actually expanding this file in memory, but just understand where we're writing to. It's kind of after the last record. And when we go to write to it, we're going to write as bytes. So using that special function we wrote to essentially step through this student object in memory one byte at a time, writing each byte of this object's in-memory representation to the file. And we're going to continue this process for size of student bytes. And again, because each student object is going to have the exact same in-memory representation based on how we defined our student type, it's just going to go through, in this case, whatever a student object size is, boom, write it, pull out that number of bytes and essentially write them to the file. So again, there are going to be many different approaches to write a collection of objects to a binary file. We could have written a function that would process a student library vector of students, similar to what we had implemented in the CSV example of the previous lesson. Here, I simply chose to append each student object to the end of the file. So, just like to create, to read, there's going to be many different approaches to read objects out of a binary file. And we're going to need an object to actually read them into. So we could have written a function that would read all the objects into a student library vector of student objects, similar to what we had implemented in the CSV example in the previous lesson. Here, I wanted to kind of show the power of seeking and go, because each of our student objects are fixed width, written in binary, technically we could move that pointer that points to the get location in the file to the record we're interested in, and then read it into a student object. And that's exactly what this read student at location function is going to do for us. So here, in this example, I've chosen to simply read one student object at a specified location. And again, you could have crafted many different ways to kind of read this. I mean, your format of just storing these objects in a binary file could have been completely different than what I'm doing here. There could have been headers with more information about offsets and other information to create a more elaborate binary encoding scheme than what we're doing here. So in gray is kind of what I'd run in main. In green is going to be the actual implementation for this read function. So I have some file, data3.dat. I have a student object, and I'm going to go ahead and assign it the return result of read student at location. This function, student at location, has two parameters. The first is going to be the name of the file, which we'd like to read a student object from. The second is going to be the location of that record within the memory. And here we're assuming this as the specific student object. So 1 would correspond to the first location, 2 would correspond to the second student object within this file. Notice that when we actually go in to get that information, it will be 0 index. So we'll offset the location that we specified by 1. So anyways, when we get into this, we're going to go ahead and bind a input file stream IFS to that file, data3.dat in this case, and we're going to open it up so in binary mode. We're then going to move that get pointer from the beginning of the file, essentially size of students multiplied by the location -1 forward into the file. If location is 0, notice here that we can stay at the beginning. So if we're saying we want the first record, so location 1 of the file, that record is going to live at, if you're thinking about this in terms of arrays, the 0th kind of index. It's at no offset from the base address, in this case, the base address being the beginning of the file. Now, if we wanted to say, get the second record, you can think about that as living at the second position in a array or at the first index. In that case, we'd have to offset that base address of the array using pointer arithmetic to get to the second record. Here, we're doing the same thing. If I said I wanted the second record from the file, I'm going to seek or move that get pointer, size of student times 1, so the actual location we want, which was the second record, -1, so that we're moving it size of student forward, and it's essentially then is going to be seated or positioned at the beginning of the second record stored within that file. And that's what this is doing. If we wanted the third record, So let's just draw this out. 1 record, 2 record, 3 record. Notice that this is at std ios beginning. This is at size of student times 1, size of student times 2. And again, if we multiply size of student by, say, we wanting the first record 1 minus 1, that's 0, that would keep us right here. And we could go ahead and read out essentially that student object. If we wanted the second record, we'd have to move size of student. So that would get us from here to here, where we could begin reading the second student record stored in the file. So the first step in this reading process is actually getting that get pointer to the proper location. Once we're at the proper location, we have to define a student object, which we're going to essentially, let's say we have student S here, that we're going to, in this case, if we're reading the first thing, that we're going to grab that record and put it into as our in-memory representation. So once we have that student, we simply say ifs.read. It will read from the get pointer, whatever that may be. It will read size of student, and it will go ahead and put the data from the file into our student object S. And then we return S, and guess what? We have an in-memory representation of the student object at that specific location in our file. Notice here I have no error checking, so I'm not doing anything to check whether or not, hey, does this record even exist? If you were to implement this, you need to think about how to go about doing that to ensure that we're given a valid location and then we're not running past the end of file marker during the seek process. I'm gonna pause it for a second. Okay, so let's say I've read in a number of different student records into my application. I'm doing something with them. I mean, you could have read in all the student records from the file into a vector of students, and maybe you kept track of which ones you modified in some way. And you're going, okay, I don't want to have to write everything back to the file. I only want to write back those that I've updated in some way, shape, or form. Well, let's say that. So I guess first, there are many different approaches to updating objects in a binary file. Here I've simply chosen to take a specific object and write it to some location in memory. So again, some location in the binary file. So I create a student, it's myself. I don't know, I do something with that student, I append it to the file. I go ahead and read that student. So this is kind of just the illusion that we had some initial data. We put it into the file. Now we're going to read it back, and assuming this is empty, Noack Michaels at position 1. So, I mean, these couple of steps are like, okay, whatever. We've retrieved the student object we wanted from the binary file. Now we're going to manipulate it in memory. What I'm doing here is simply updating the first name from Michael to Raymond. And then what I'm going to do is write back this student object to the first position in memory. And I could have specified something else, and obviously I don't have any error checking here, which again, you need. But assuming one's a valid position, my rewrite student at location function will take the file that we're writing to, the location within that. Again, so 1 corresponds to the first record in the file, 2 to the second, similar to the first element in an array, second element in an array, and then the object that we're writing. So I go ahead and I open up a output file stream because, hey, we're writing to a file. OFS gets bound to whatever is used to initialize my file parameter, and I'm opening in binary mode. I go ahead and seek to the position where I'd like to write to. And this is going to be some sort of offset from the beginning of the file. We saw this earlier. At this point, you should understand what seekp is doing. It's, starts out at the beginning of the file here, and it's just moved forward some number of bytes. So the size of student number of bytes multiplied by the location -1. If we're adding to the first record or updating the first record, that put pointer is not going to be moved forward. It's just going to stay at the beginning of the file. If we'd like to update the second record in the file, it has to move past the first one. It will be beginning at where the second record is actually written in that file. Once we seek to the proper location, we're simply going to write that student out to that location of the file as bytes. So we go out, we grab our in-memory representation, byte by byte, we're putting it into the file. So boom, 1 byte, 2 byte, 3 byte, and it's just being copied over from in-memory byte by byte into our file. And the number of bytes being copied from memory are going to be essentially the size of student. And because this is all fixed width, if we're updating at the first location and we're updating the size of a student, we won't inadvertently run into the second record because each student record is going to be the same size. Likewise, because each one is the same size, we can seek past one, get to the second record, get to the third, whatever. And then we can begin this updating process or transferring, essentially going byte by byte from the in-memory representation to our binary file. So again, I don't know if I said this, but there are many different approaches to updating an object in a binary file. The one I've chosen here you have to do a couple of steps. You have to actually read it. You might combine these, you might keep them safe. There's a bunch of different ways to go about this, many different ways to code this. And in all honesty, we probably would have been better off to write a class that had all this functionality encapsulated under one roof. But I think it's easier to just look at these functions kind of one by one without the overhead of having to remember it's okay, we're dealing with it. Well, what's the class doing, etc. So again, here I've chosen to simply read a specified object from a file, we get it into memory, we update it, and then we write the result back to the same position in the file. And just to say that's what I'm doing here, but you could have theoretically wrote that student object back to any valid location within the file using my rewrite student at location function. So I know we're running a little bit longer here. I know the past couple of lessons might have been a couple minutes longer than what we were anticipating for. So I'm going to go ahead and leave. We went through all this. You have a good idea, hopefully by now, is how to move through the file, move those put pointers, the get pointers to proper locations, read and write. And I'll go ahead and say, okay, turn it over to you. How would you implement functionality to delete a record from a binary file? And with that, I'll go ahead and close this out. The next lesson is going to be an introduction to relational databases, where I'll kind of introduce some data that's not a flat structure and go, well, how can we organize this? The plain text doesn't seem to be reasonable. Binary seems to have kind of some issues. Well, how can we express those, relationships in different ways in more complex data structures? And we'll go ahead and get into how relational databases can help in good form of persistent storage for more complex objects. So that ado, I'll see you next time.